next, we're going to go across to Bristol, and we're joining Neil Fox and Gary Wan, who run the Bristol nanoESCA facility. So we're going to find out what nanoESCA means and hear a little bit about some of the research that takes place in this laboratory.
Hello, this is Gary. Thank you for having me. And yeah, so today we'll be showing you a quick tour about around the Bristol nanoESCA facility, which is, I think, the only one in the UK and one of the few in Europe. But unfortunately, the lab is actually in it's in an ultra-quiet lab, so one of the quietest labs in the world. And in the Bristol nanoESCA lab, it's actually the whole thing is a Faraday cage, so there's no Wi-Fi or internet or phone signal that goes down there. So I had to pre-record a video, and I'll show you now on my computer and walk you guys through it. So yeah, this is the Bristol nanoESCA facility, which is actually a combination of a lot of instruments together. So we need quite a few computers to run everything in series. And as it's one of the ultra-quiet labs, it's actually sitting on a very heavy, large steel slab, as you can see down here. And that's all sitting on a compressed air platform, so it decouples it from the rest of the building and makes sure that it's very vibrationally stable. So what we do here in the Bristol nanoESCA is, I guess you can call it a materials characterization tool. So we do a lot of surface characterization, where we look at the atomic and electronic properties of samples. And to do that, because we're using electron spectroscopy techniques, which have extremely high surface sensitivity. So if there's any contamination on the sample surface, basically all you'll be looking at is the contamination. So how we achieve that is by making sure everything is in ultra-high vacuum, which means there's basically no molecules of air around, which can't form monolayers of contamination on your sample surface. So everything here, So everything here is roughly at 10 to the negative 11 millibar of pressure, where 10 to the negative 11 millibar of pressure is roughly 100 trillion times lower pressure than atmosphere. And that, of course, guarantees that everything can stay as clean as possible during the analysis. So you may be wondering, so this is the pressure that we're running at, as I just mentioned earlier. But yeah, you may be wondering how we actually get samples into the chamber. So if you're guessing that once opening the chamber to atmospheric conditions, it'll mean the whole chamber gets contaminated because air molecules will stick to the stainless steel chamber walls, and it'll take forever to pump back down to the pressure we're currently at. That's correct, because you always, in these ultra-high vacuum chambers, you always want to keep them continually pumping and under vacuum and never expose it to air. So what we do here is, if you look at this small chamber on the bottom, it's all connected to the rest of the chambers, which are all under ultra-high vacuum. But there's a series of gate valves involved. So, so this guy here is where we put in samples, and only this tiny chamber can be exposed to atmospheric conditions. And the rest of the samples, once put in, can be, once we put those in, we can pump everything back down to ultra-high vacuum and open the gate valves to allow samples to be transferred and quickly close the gate valves again. You can see in here, there's 3 sample slots where we can put samples in. And the way we move it is by a magnetic arm, which means we can move things from the outside without contaminating or affecting the vacuum integrity of the system. So what I'll show you now is a little in-house built chamber that we have, which is also connected through another gate valve, as you can see. So this guy is what we call a fabrication chamber, where we do a lot of sample preparation, sample modification, and creating new samples, basically. So on the bottom, you'll see what I'm pointing at now is this is an electron beam evaporator, where we can evaporate different types of metals, different types of materials onto the sample surface. And so the way that we calibrate how much material we're putting onto the sample is through something called a quartz crystal microbalance. So what I'm pointing at here is actually a crystal that vibrates at really, really high frequencies. And anytime anything gets absorbed on the surface, so when we're evaporating metals, the vibrational frequency would change very, very slightly. And because it's super, super sensitive, it can measure down to single atomic layers of material. We can use that to calibrate how much we're evaporating and at what rate. So the samples we're preparing, we can put single atomic layers or even less partial layer coverages and measure the electronic properties of that. So if you look into the chamber itself, we're now looking through a glass panel, a glass viewport. So in the center there is where the sample would normally sit. And that can freely rotate and move around. So when it's pointing downwards towards the bottom hole, that's where the electron beam evaporator is. And the one at the top, you can see sticking out a little bit. That's where the quartz crystal microbalance is. And at the center there, the copper piece sticking out is actually a gas cracker, which means we can flow in gases and excite them to atomic radicals, which can basically, so we would flow in gases through this valve here. And that induces chemical reactions on the sample surface. And this can all be done in situ. And the sample can be prepared while in ultra clean environments and then be moved on for characterization. So if we look at one of the main characterization chambers now, so this guy, this is where the sample can be transferred to, and it will be placed in the center manipulator, where it's a very, very long arm that can move backward and forwards and to different characterization techniques. And things are moved around by a wobble stick, which is the one I'm moving right now. And it's basically a clamp, an arm with a clamp that can move around and hold the sample, move it around to the different positions. And that's, again, all done by this magnetically controlled wobble stick. So now I'll walk you through one of the main characterization techniques, which is called X-ray photoelectron spectroscopy. This is basically taking full advantage of making full use of the photoelectric effect, where you shine photons onto a sample, electrons absorb the photons and become higher in energy, and they come out of the material. So these core electrons that are deep inside the atom will excite with X-rays, and we'll look at the electrons that come out, and that's how we analyze the surface properties of the material. So what we're looking at now is the X-ray gun. So this is the X-ray source, where it's actually generated by an aluminum target, and X-rays come out of that. And then they go through this huge monochromator here that focuses and filters out energy we don't want. So it guarantees that the only photon X-rays that come out are very specific energies and well focused onto the sample. And once that happens, a lot of electrons come out, and we have to detect and analyze those electrons. And that is done by this huge hemispherical electron analyzer here. Basically, electrons will come out through this channel, go into the hemisphere, and they'll curve around towards the detector, where the detector is at the end here. This guy. So as you can imagine, so the electrons that go through the hemisphere are going through, they see a lot of electric fields, and they basically are forced to curve, depending on their energy. So if they're very high energy, they have a larger radius of curvature, and if they have lower energy, they have a smaller radius of curvature. So that's how we determine the energies of the electron. And once we know the kinetic energy, because we know the initial photon energy, we know the energy at which the core levels the electrons were sitting at in the material. And we can do a lot of elemental fingerprinting, for example. So I'll show you some examples of spectra of electron spectroscopy. So this, for example, is a sample of carbon, where you have a huge peak here, the really, really big peak. This is from the carbon atom, while this slightly smaller peak is from the oxygen. So we know that the sample, really quickly and really easily, we'll know that the sample has carbon and oxygen on it. And if it's a more complicated material, we can look at the sizes the ratio of the sizes of the peaks, and we'll determine what ratio of the atoms are on top. So we'll know basically the chemistry and stoichiometry of the sample. And I'll move on to another example here, where this is a copper crystal. So as we know, copper has a lot more electrons than carbon. So you see a lot more peaks of varying intensities as well. So again, this is because of all the core electron orbitals within the copper, and they show different peaks. One other interesting thing you can know is that the chemical environment actually changes depending on different absorbed molecules or gases on the top of the surface. So with this technique, we can see the peaks shift very slightly, and we can know roughly what things are bonded to. So this is also a chemical environmental test as well. Another technique we do in this chamber is something called X-ray low energy electron diffraction. So basically electrons act as waves, and as some of you may know, waves can actually diffract depending on what they hit. So the surface of a sample would have a lot of atoms on the top, and those atoms are arranged in a very orderly fashion sometimes. And because of that, they cause a very orderly diffraction pattern to come out. So in the center, you see this diffraction spot, which is from electrons being diffracted and coming out in the center. This spot itself would have would just show that we have a very orderly sample. And on the outer regions, you'll see 6 other spots. And the distances between the center one and the outer regions tell you the distances between the atoms on the surface sample. And the arrangement of these spots will tell you the geometry, basically, of the sample. So we know this has a 6-fold symmetry on the sample surface. And if you look even more closely, you'll see that around each center spot and the outer spots, you'll see 6 smaller spots around it. These spots are because of very small fluctuations of the order of the sample surface. So, for example, as I mentioned earlier in the chamber where we can evaporate stuff, sometimes when you evaporate gases or evaporate materials onto the sample surface, they'll form chemical bonds, and these bonds very slightly change the orientation or the geometry of the sample surface. And these very slight changes in bond lengths and angles would have a very slightly different diffraction pattern. And this is what we generally call surface reconstruction. So here you can see the surface are reconstructed slightly, as you can see more than the 7 main spots. And combined with the X-ray photoelectron spectroscopy, this gives you a very, very good idea of what's happening on your sample surface without actually looking directly at the atoms. So we know what kind of material, how they're bonded, and the order of how everything is. So now I'll quickly move on to another technique that we use, which is UV photoelectron spectroscopy. So it's very similar to the X-ray photoelectron spectroscopy, but instead we're using UV light. So what I'm showing you here is the UV lamp. It's actually a helium plasma discharge lamp that shines light directly onto the sample. And I'll go around to where the sample analysis is done. So here, we're basically going to be looking at bonding electrons. So no longer looking at the core electrons within the atoms, because those require X-rays to excite. And these are much lower in energy. However, in my opinion, they're much more interesting electrons to look at because they're bonding electrons, so they have much higher dispersion. They usually have positional dependence because of the way they're bonded, the angles at which they're bonded, and they're usually hybridized with each other. So these are the free electrons flying around in the material and not just sitting in the very core levels, not interacting with anything. So a lot of material electronic properties are actually completely or entirely based on these electrons. So that's why they're quite an interesting thing to analyze. So what I'm looking at here is the electron energy analyzers. So you actually see 2 hemispheres here instead of the one previously seen with the X-ray photoelectron spectroscopy. So what this gives us is electrons basically have to go through both. As they curve through both hemispheres, we have a much higher energy resolution. And the most important thing it does is it actually reconstructs an image back. So we're not just looking at energies, but we're actually seeing an image reconstructed back onto the detector. So this can basically act as a electron microscope. So this is the path they go through, and the camera's at the end. So we basically have an electron microscope, and at the same time looking at the energies of the electrons. So one of the things we can use that to do is looking at the work function map. So this is a false color work function map using the double hemisphere detector that we have. And basically each color represents the different work functions across the sample. So each pixel has a different work function, as you can see. And the sample, because of the hugely varying work functions, you can know that it's not a very homogeneous sample. And that could be due to the fabrication technique, which is very useful for people trying to make new materials. So if you want it to be a very homogeneous sample, looking at this, you'll know that, oh, you need to alter your method very slightly. But in this particular material, which was, I believe, it's used for conversion of solar energy to electronic energy, you want some of these different defects and different work functions for it to perform properly. And these can be done with different alloying of the materials. So when the atoms form alloys, the electron work function changes slightly. And when you have different absorption of materials on top, the work function also changes slightly. So it's a very good, powerful tool for imaging, as well as knowing the work function differences on the sample. And however, in physics, a lot of people are more interested in something called the electron dispersion relation. So on the blue image here on the left, this is actually a silver crystal. And we're no longer looking in real space, so a microscopy image, but rather something we generally call K-space or wave vector space. So electrons in materials, they actually behave as waves, and it's more useful to image them directly as their wave function. So looking at the bright spots, the bright areas in the blue image on the left, we'll know where the high electron densities are, and those tell us the direction at which the electrons are traveling. So you see a lot of electrons traveling in all sorts of directions on this crystal surface, which tells us that the silver is in fact extremely conductive, and it has a lot of high density of electrons, which is exactly what we know. So this tells us why silver may be conductive and why it has the properties that we generally see electronically. I'll show you another example of a copper electronic band structure, which is this guy here. So now this is during a scan where we're looking at different energies across the whole dispersion relation. So I'll scroll through the energies, and you can see that the electronic bands change very drastically. So this is their dispersion relation. So as energy changes, electrons move in all different sorts of directions. And at the very highest energy, this is very roughly at the Fermi level, which is where the highest electron energies sit at. And here is what we call the Fermi surface. So almost all the electronic properties actually originate from the Fermi surface in a material, because these are where the electrons have the highest energy and they're allowed to move freely around without being blocked by other electrons. As copper is actually a very well-known material, but if you look at new materials, you look at their Fermi surface and you can determine a lot of properties like how good their conductivity is, whether it's an insulator, whether it's a semiconductor, and how big the band gap is. And as I mentioned earlier, during the fabrication technique, if you add maybe a partial monolayer coverage of materials, that could change the band gap and the conductivity and how the electrons move in the material. So all this is a very useful technique and very, very powerful to look at electronic properties with the new materials and generally for the material characterization community. These things are extremely useful and powerful to help predict and generate new materials for the future. Right, so that
thank you, Gary.
Concludes quite well.
That's fantastic. Really good, and well done on the creative solution of how to do the tour in a sort of a Faraday cage by preparing in advance your virtual tour.
Yeah, actually, the funny thing is we don't actually need the Faraday cage function because, as you can see, the whole chamber is a big stainless steel thing, so nothing will really affect it. However, this is one of the ultra quiet labs in Bristol University, so we actually have a lot of people doing quantum information tests, so any sort of stray photons coming in from the background will affect the measurements. But for us, it's more of an inconvenience because you can't use your phone while doing labs, which is sometimes good, sometimes bad.
No, fantastic, and that gave a really good insight into some really complicated equipment, vacuum equipment that's got to be maintained, used for really high-level advanced science. So thank you ever so much for that, and also to your colleague Neil as well, Neil Fox, for helping to facilitate that. That's really fantastic.
Yeah, thank you very much.
Thanks, Adrian.
Thank you. Thanks, Neil. Brilliant.